Welcome to 2025, everybody. Yeah. That's right. That's right. We got to get as nerdy as possible, right? Yeah, so 25 squared, right? What? 24 squared. 45? Is it 45 squared? Can someone confirm that? Wasn't it something like, did someone do 20 by 25 or something? There's some other math you could do on it. Can someone verify? So 45 squared, we know what you're doing. Anything else we got? Okay, well, thank you. Math professor, he's the nerd, he's chief nerd right now. See if we can outdo him. All right, so first up, before we get even nerdier than we already are, is anyone hiring? Is anyone looking to hire somebody? Someone's hiring in person for once. Come on up here, tell us what you're hiring for.
Cool. Mike,
wait, isn't your whole job over now? The elections are over?
Surprisingly, no.
All right, so can you hear him? Hopefully people can hear you.
Okay, mic check if you're at home.
I can unmute this if you want to talk into this one.
Oh, they can hear you.
Okay,
it has
cool.
good pickup.
Okay, cool. Hey, I'm Andy with Grow Progress. We're a progressive consulting firm that helps candidates, PACs, and nonprofits test their messages and learn what works. We're actually hiring, so I'm a data scientist, but our engineering team is hiring right now. We're hiring 2 associate software engineers, so the stack for that is like Node, Vue, Laravel, that sort of thing. If that sounds interesting to you and you want to take a look, you can find us at growprogress.ai. If you want to talk to someone at the company, feel free to send me an email. I'm Andrew at growprogress.ai. Yeah, come check us out. We do great work. We have a lot of impact. It's a good time. Thanks.
All right. Good. Someone hiring in person. Yeah, round of applause for that. Someone's hiring. Is anyone else hiring? Yeah, seriously, it's been really bad. We used to get like 10 people offering jobs. Anyone else want to offer someone a job here? All right, you don't have to, no pressure. But you're hiring. Can you post on the jobs channel?
When I find that, yes.
All right, so for everyone watching virtually, or anyone here who doesn't want to do it in person, or for you, if you go to the nyhackr Slack, are you on the nyhackr Slack?
No, I should probably.
Yeah, so go to nyhackr.org, go to the Slack channel there, use a link, it just automatically makes you a member. There's a channel called Job Postings. Or it might be Jobs Postings, no, it's Job Postings. And go in there and post your job and get people to come apply for your job. Even though very few people are actually ever hiring in person these days, we still get people posting on that channel. So likewise, if you are looking for a job, either be in touch with Andy, or go to job postings at the nyhackr Slack and find a job someone posted up there. People are still posting up there despite not being here in person. We are an international group all over the world, so find your job wherever you may be. Since we may not be hiring, but we all have to eat, the pizza today is from John's of Bleecker by special request of tonight's speaker. Yeah. So, yeah. So everyone who knows this routine, everyone who doesn't know the routine, you'll learn it. Go to bit.ly/pizza poll, all lowercase, and rank the pizza. We have a 5-point scale, essentially 1 through 5. It's not quite a Likert scale.
Very fitting for what we're talking about today.
Yeah, see, there you go. See, it all ties in. It's been 15 years in the planning for this talk. But go in there. We've been collecting the data for about 13 years, maybe 12 years, with a gap during the pandemic, and vote on the pizza. You have a question, or just raising your hand? Not raising your hand.
What's the highest rated pizza?
Ooh, so you can get the data. You can get the data live at jaredlander.com/data/pizzapoll.php. Yeah, seriously. And it comes as a JSON feed, and you can analyze it. But if you also go to nyhackr.org, there is a live bar plot, a JavaScript bar plot, and you can slide across it and see which one is so far the highest. It's a distribution of all of them. So you can check it out there, or you can do your own analysis.
Great.
Data is freely available. I think the P in pizza and poll are both capitalized. But if you go to jaredlander.com/data, you'll find it. Yeah. It's a live feed. As people are voting, the data will change. It's pretty cool. Yeah. It's like a back-end Postgres no, it's a MySQL database, and it's a whole mess that I built 10 years ago, and if I touch it, it'll break. Yeah. All right, so those of you that don't know, those of you who are normal regulars here, you know this. Noam, did you vote? All right, good. Those of you who are my regulars, you know this, but my new folks here, go ahead and vote on the pizza. Those of you watching from home, I know you can't be enjoying New York pizza unless you happen to be, I guess, in New York. And we do know there's some people from NYU watching from home, right? But if you're at home, tell us what you're eating. So go on the YouTube channel and let us know in the comments. Or go to the Slack. We have a Slack, that same Slack for the jobs. You go to monthly meetup chats, and you can tell us what you're eating. Whatever you're from, whether you're drinking something, eating something, just be a part of the food community inside this data community. So let us know. Then, speaking of people who don't know about the pizza poll, who here is new? Raise your hands. Cool. How did you hear about the meetup?
colleague told me.
A colleague told me. That's a great answer. Was it him? Okay. Anyone else?
I learned from him.
Nice.
He's my professor.
Oh, nice. Oh, nice. All right, great. You're the ringleader. Or the Pied Piper. Yeah, you have a little flute, right? All right, anyone else new who wants to share how they joined us?
Found it on meetup.com.
Okay, that's a good entry portal. Great. All right, where? George? George told you? Okay. Well, he made you come. Did he threaten you?
No.
Okay. Okay, are you a student? Okay, because he told his students they don't get A's unless they show up. So that's a joke in case anyone's watching.
I definitely did not say
All right, but welcome to have you all, you new folks, old folks. You've been here for a long time. Everyone to hang out. This is new folks. This is a really great community of really great people. I've known people here for 15 years. Really great friendships in this group. So happy to have all you folks and happy to have all the returning folks. And again, if you're new, the pizza is really important. Next month, we have it scheduled. We're going to get the exact date lined up. Depends on some travel schedules. We have a really cool talk about subway stories, about how you map people's journeys on the subways. The MTA has a model built to try to predict where you're getting off of the subway. So we have speakers coming. Jediah, is it Jediah and someone else, or just two people? Jediah and who else? Jediah and Friend. Well, sorry, Friend, I don't remember your name right now. I didn't look at the note Nicole gave me. But talking about how they made these maps and the choices they made during the mapping, how to present the data. It's going to be really, really cool. This is our second subway talk in a few months. It's, we're New Yorkers. We have to ride the subway. All right, then in March, gets a little iffy. Depends if our speaker gets approval. There might be that talk about Pixar. Eric is not here. He's getting sick of me saying, do you get approval yet? If it's either going to be him or it might be Vikram. And whoever doesn't speak in March will speak in April. So either Vikram and Eric in March, one about Pixar, one about something else, and it'll be the other month. We have May and June kind of organized. Garo just reminded me he's speaking in one of them. We have Paul Yang speaking in another. We might have someone else. Noam's going to be speaking in July, roughly. Yeah, don't look at me like that. You're speaking. So if you want to speak beyond July, come find us. Say you want to give a talk. Otherwise, I have to call on you randomly at the start of a meetup, and then you have to say yes. So tell me you want to give a talk. It's a big tent. We have topics on R, Python, Julia, SQL, Go, Rust, C++. It could be about a mathematical talk. It could be an applied talk. It could be about databases. If you look at our history of talks, it's a lot of different talks. There's tons of options. If you want to see some of those talks, go to nyhackr.org to find all of the old talks for the past 15 years. Some of the years we only have slideshows. Some years we have videos. Other years we have decent quality videos. So check it out. And to go with it, we have a conference website, rstats.ai, with 10 years of talks from one conference and 7 years of talks from another conference. So there are a lot of videos out there for you to learn from. They're really cool. Some of them are classics that people are watching 10 years later. Some are brand new. A lot of really good options. So check out those resources for you. All right. I told you to check out our Slack. Now, if you have questions for this talk, if you're in the room, you can just raise your hand and interrupt whenever you want, or at the end.
Yeah, they can interrupt.
Interrupt whenever you want. But if you're watching virtually, if you put your question in either the YouTube chat or the Slack, I will collate those talks, weed out any weird ones, and then, yes, that's happened before, and then usually when no one speaks, actually, it's funnily enough. Sorry, I know I'm picking on you a lot today, but you're here. I never get to see you. But seriously, though, I will ask your questions of George at the end. I'll collate the questions and ask the questions. So if you're virtual and you want to participate in questions, go ahead and join us. All right, one last announcement before we get to it. We, as always, everyone knows this who's regular, new folks who are learning this, we are going to go to the bar afterwards. We have pizza, we have a talk, we go to the bar. If you don't drink alcohol, come and have a soda or have food or have water or whatever else you want. It's about being there and chatting with each other and hanging out. It's just a really fun time. We just like to hang out and be nerds together, right? You're in a room full of nerds. It's too cold to go home. Might as well go to the bar. All right. We will announce which bar it is later because George and I always like to argue over which bar we're going to go to. I'm like, George, what do you want? He says, I don't know. I'm like, thanks. So we will find a bar for you, possibly Vol Denis, possibly Malt House, possibly something else, and we'll pick a bar that's close enough so you don't freeze, and we'll go have a nice time. Cool? Who's coming to the bar? No pressure. Yeah, cool. All right. And I'll ask again later. We'll announce the bar officially. And with that, we want to say a big thank you, actually, to NYU, where we're all hosted, particularly George, for getting us, big round of applause for George. NYU has been our consistent home for about a year and a half.
Yep.
About a year and a half, a little more than that even, a year and a half here.
Yeah, since October.
October?
24.
It was before then even, I think. You did one, you did a few, one off or two off.
Yeah, we did a few one-offs.
And at 23, I think you meant.
Yeah.
Right, but it's been here for a while, and that's George to thank. There's a lot of other people at NYU who have been involved. Yeah. Yeah. But seriously, George is the reason we have this beautiful home here at NYU. It's been consistent. He has this great space for us. We might be starting to grow out of it. All right, so it might be freaking awesome. We have to get a bigger room, that's all.
There's other rooms?
There's other rooms. But seriously, George is the reason for this. And to thank him, we're making him give a talk again. So he actually, one of our first meetups here, we made him give a talk. It'll be like an annual occurrence that he has to give a talk. So everyone please welcome and enjoy all the causal inference goodness. Did you spell causal or casual?
Causal, I don't mess that one up.
All right, causal inference. Thank you very much to George. Big round of applause.
All right, well, thanks everybody for coming. So I'm going to talk about a new idea, something I've been thinking about since the summer, maybe October even, called measurement-induced confounding. Usually I've given a bunch of talks here talking about BART, machine learning, and causal inference and estimating causal effects, and it's very positive, it's very yes we can. Today may be more of a maybe we can't. So this is very much a new idea. I'm thinking about how to talk about it, so excited to share it with you. So before we get going, we're going to have to formally define, like, what does it mean for something to cause something else? We all have a lot of ideas about causality, but what does that actually mean formally? So we're going to consider a single person. So we have this worker, let's say in 1975, he takes home $20,000 in earnings. Now, he enrolls in a jobs training program. A couple years later, in 1978, he becomes a welder and is making $30,000. So a claim we could make from this, or a claim a lot of people like to make from seeing things like this, is the jobs training program has caused this worker's earnings to increase. Now, that may be true, but not necessarily so. We don't fully understand if this program caused a change in income without thinking about what would have happened had they not been enrolled in this jobs training program. So it's certainly possible that the same worker, had they not enrolled in the jobs training program, they would have kept the same job and their earnings would have remained the same. So in this case, enrolling in the program appears to have led to an increase in earnings. But there's a lot of other possibilities that could have happened. It's possible that economic conditions could have changed, and he would have lost a job had he not enrolled in this jobs training program that diversified skills, kind of enabled new opportunities. And so this would lead to a much different impact from the program. Likewise, it's also possible if he remained at his current job, he would have been promoted, maybe became, if he's a construction worker, say at the beginning, maybe he becomes the foreman or the leader of many construction workers, and would have actually made more than had he enrolled in the jobs training program. I'm going to take this opportunity to introduce some notation I'm going to be using later on. So in the causal inference space, we usually use a big, bold X to represent pre-treatment variables, basically things that we know about people before the intervention in question begins. Let's say this jobs training program happens in 1976. Things like somebody's earnings in 1975, that would be a pre-treatment predictor. We usually use X to denote all of those things. Z, by convention, is generally used to represent the variable relating to the thing we want to make a causal claim about. Z equals 1 generally means the treatment or receiving the thing. In this case, Z1 means that you got the jobs training program. And Y1 is going to be your outcome, in this case earnings in 1978, if you had enrolled in that treatment. Conversely, Z equals 0 represents that you did not enroll in the program, you did not take the drug, you did not do the thing. And Y0 is what would have happened to you under that course of action. And we also call the factual outcome what we actually observe. In this case, this individual, they actually enrolled in the program, they became a welder, they made $30,000 in earnings. This is the factual outcome, we can see it, and we can actually know that to be true. The counterfactual outcome is what would have happened in this parallel world had the action been different, had they not enrolled in the program, had they not taken the drug, if this is a medical study. And there's many possible counterfactual outcomes. In fact, there's an infinite number of them, and we don't know what these are. We do not know what would have happened to this individual had they not enrolled in the job training program, because we only see the world in which they did. And this is what's called the fundamental problem of causal inference. So an individual causal effect, it's the difference in these two potential outcomes, the factual outcome and the counterfactual outcome. And it's usually defined by just the difference between them. So the effect of the jobs training program is, well, what is their real earnings under the program subtracted from what their earnings would have been had they not enrolled in the program. And the problem is we don't know what their earnings would have been if they didn't enroll in the program. And this makes individual causal effects non-identifiable. That's a technical term for essentially saying we don't know what they are and we have really no way of estimating them reliably. All of this is in the case of a binary treatment. You're either in the program or you're not, but it generalizes to multi-arm treatments too. So this seems like a big intractable problem. How can we actually make causal claims about things? And the answer is by using more people. So if we have a lot of folks, and some enrolled in these jobs training programs and others didn't, then we can make a claim about the average treatment effect. So usually we are estimating the sample average treatment effect. So for a group of workers, some of which who enrolled in the program, some of which who didn't, what is the average effect on real earnings? And we can think of this as just the average. This math notation, it's just a fancy way of saying the mean or the average of all of the individual causal effects. And this is identifiable under certain assumptions being satisfied. Now, ideally, the best way to estimate the state is running a randomized study. Randomized studies are great. If you take nothing away from today, other than what I'm about to say, the most important thing is if you have a choice and you're trying to make a causal claim, you really should do a randomized study. All of the issues I'm going to talk about later on, they do not apply to randomized studies. So if you ever have a choice, make sure you do one of these. So I opened thinking about real earnings and job training program because this is something that actually happened. So there's something called the Lalonde study, and it was a randomized study on labor economics. And they wanted to estimate the average treatment effect of a jobs training program. They had 445 men enrolled in the study, and they randomly assigned them to either receive the program or to not receive the program. The outcome was, of course, real earnings in 1978, and they collected a bunch of pre-treatment information, too, about all the folks in the study, things like how old were they, what were their earnings in 1975, were they unemployed or not, what was their educational status. We have the same kind of economic indicators in 1974. How much were they earning then? Was it the same as 1975? You could see maybe they're on an upward trajectory, maybe they're on a downward trajectory. Were they married or not? Did they have a high school degree? Very traditional kind of labor economic variables that we have ideas of how they relate to earning potential. Now, what's so special about randomized studies is on average, we know that the distribution of all of these variables are equal between the folks in the jobs training program and the folks who are not in the jobs training program. So here's the distribution of, I picked age because it's an easy variable to understand. And these two distributions look very similar. Now, they're not identical. There's a little bit of a difference. We see the folks in blue that kind of represent not receiving the program. There's a few more of them who are younger, but the general shape is the same. So it's not true that there's no differences between the groups in your study. But what is true if we think in expectation? And so what do I mean by that? This is, because this is the R meetup, I have to have some R code and some notes here. So let's imagine if, because I know kind of the assignment process, I know that we basically flipped a coin to determine who got access to the program and who didn't, we could just continue to kind of re-randomize and look at the distribution of age. If we did this, in this case I did it 10,000 times. So we're approaching expectation, we'll never really get there. But when we imagine redoing the randomization again and again and again and again, we see these distributions begin to converge, they converge. And now they look nearly identical. I cannot distinguish between these two distributions. And as we take the number of re-randomizations to infinity, they'll become perfectly identical. And so this is what I mean when I say there's no difference between distributions between the treatment and the control in expectation. So if we re-randomize again and again and again, we know things like age will be exactly the same between the treatment group and the control group on average. And this is a really, really critical property. This is really what's so special about randomized studies. Because it turns out that's not just true of the variables we can see, things like age. It's true of all variables, including the ones that we can't actually have access to. So the distribution of number of cats is the same between the treatment group and the control group in expectation. Same with things like motivation, interest, latent ability of any trait, and most importantly, the distributions of those potential outcomes are actually the same. The things that we can't observe, those counterfactuals, are actually the same between groups. And this is what's so critical about randomized studies, I should say. So under pristine randomization, all variables, y is different for complex reasons, because in the causal inference space, y is not really a variable, it's a function of two other variables. They're balanced across treatment groups, in expectation, of course. And so this is true for things like age. Colloquially, this is described as there's no confounding variables. So there's no confounders that exist. But what's really important from a causal inference perspective is we can see the Y1s. We can see the real earnings in 1978 if you get the jobs training program for the people that got the treatment. So we can see that variable, but we're missing the other half of the variable. Because of this balance property, we know that the unobserved part of those Y1s is actually going to be the same as the group we can observe, on average. And the same thing holds for the other potential outcome, Y0. We only see the Y0s of the folks that didn't get the program, but we know that variable in expectation is the same as the one that we can't see. For those of you who are more technical, you can write this formally like this. Again, that the distribution of y1 is the same conditional on z1 and z0, likewise for y0 as well. There's some other structural assumptions too that aren't particularly relevant for today's talk. If you've heard of things like SITVA, we have to assume that's satisfied as well. And there's also some baked-in assumptions about missing data, but this isn't to talk about either of those things, so just note that those are there. Okay, so why do we care about this property? So I've slightly augmented our data to resemble the real problem we have in causal inference. We don't really care about this outcome y. We care about the difference between y1 and y0. And when we actually do data analysis, we're missing a large swath of our data. So all of the folks on the screen right now received the program. We see what happened to them under the program. And we have no information about what would have happened to them had they not received the program. And if we go further down, we can actually see people that didn't see the program. It's the opposite problem. So for these folks, we see what happened to them without the program, but we don't actually know what would have happened to them with the program. So what this balance property allows me to do, I can just basically group by the treatment and take the mean of the outcome. And this is showing me the y1s I can observe and the y0s I can observe. I can just take the average of those, and I can plug it in for the missing information. And this is, in effect, one of the things we can do when we analyze this type of data. And we know that, on average, this will be an unbiased estimate of the sample average treatment effect. Because these distributions are going to converge in expectation, I know that the average is not going to be wrong in either direction, which is going to give me an unbiased estimate. And so when we analyze data from an RCT, we know that, on average, it's not going to be biased. And we can use all of the theoretical properties of statistics to derive things like credible intervals to basically make claims about how confident we are in this estimate, if you're a Bayesian at least. There's similar properties if you're a frequentist, but the implications are a little bit different. So in the case of the Lalonde study, on average, this jobs training program, it led to an increase in about $1,600 yearly in real earnings. In 1978, that was a lot of money. So this is a good news for public policy and suggests that these types of interventions work, and we really ought to be putting them into practice. So this is all great. Randomization is fantastic, but it comes with some caveats, mainly that it's not always possible. And there's two reasons why. The first is there's a lot of ethical constraints that prevent us from doing randomized studies. Let's think about the case of going to college. We've been thinking a lot about real earnings. If we really wanted to know if going to college increases real earnings, we could do a randomized study where we take a lot of folks, we randomly assign which ones can go to college, and we actually force them to go to college, and then the ones who are randomly assigned not to, we make sure they're not allowed to go. Nobody would agree to such a thing. It would be very, very unpopular. In the cognitive psychology world, there's a lot of interest in language development. How do humans acquire language? And there's a very developed theory that learning language requires early exposure to a language. And then if you miss out on being exposed to language in this critical window, you will never have the ability to learn it. And so what we could do is we could randomly assign a group of folks from birth never to be exposed to language until, say, like age 10, and another group would be randomly assigned to be exposed to language. This is, of course, hideously unethical and should never be done. And so these are just a few of the many examples of when we really can't randomize for ethical reasons. And even when we can and there's no ethical constraints, there's all sorts of logistical constraints that prevent us from doing those. First of all, as somebody who's done a lot of randomized study work, they're very expensive and very time consuming. And it's also very hard to kind of get buy-in for it, even when it's ethically permissible. And then also participation in these things, the folks that actually sign up to be in randomized studies look systematically different than the participants that we're oftentimes interested in. This is a really big issue in drug trials. The types of folks who enroll in drug trials look very, very different from the folks that actually are given the drug ultimately. And that creates all sorts of other challenges in terms of generalizability. One thing that's often kind of not discussed is the sample average treatment effect is specific to the actual sample in the study. And it's a different thing if you want to make claims about a different population of people that are not that sample. And the SATE from one group does not necessarily generalize to the SATE of a different group. Okay, so because they're in sometimes ethically undoable and should not be done, sometimes they're logistically annoying, observational studies are a really important tool that we have. Now, they're certainly less optimal from a statistical standpoint, but sometimes it's the only option we have, and so we ought to try to do them as well as we can. So a lot of what we've learned about observational studies comes from this Lalonde study. It was a very, very important study in the history of causal inference. And so Lalonde was a labor economist, and he was very, very cynical of a bunch of the observational methods that existed at the time. And so he had access to this original randomized study, and the variables that were collected in the randomized study were actually the same variables that were collected in a national survey called the Panel Study on Income Dynamics. And so what Lalonde did, he did a really clever idea, where he took his control group from the randomized study and essentially threw it out. So he gets rid of the control group, and then he uses this national survey data as the new control group. So it's called the constructed observational study, and the idea is he's done this RCT, and so he has a benchmark of how well it worked for the folks in the treatment group. And now he's constructed an observational study with the same people in the treatment group. So he knows for these folks in the treatment, on average, how much to help them. And he wanted to attempt to recover this effect using kind of the traditional observational methods that existed at the time. Notice the PSID, it collects the same information as Lalonde had in the original RCT. Now, observational studies do not have that same balance property. And so if we look at the distribution of age in the observational study, these distributions look noticeably different. And I can't do the trick where I try to re-randomize it to take it in expectation, because a random assignment is not what determined who was in which group and who was not. In fact, I don't really know what determined that, and so I can't actually take a look at what these distributions would look like as they approach expectation. But I feel very confident in saying that they will not be the same. Simultaneously, age and real earnings in 1978 are also correlated. We see this kind of quadratic function where as people get older, their real earnings go up, and then it kind of plateaus. And eventually, as they exit the labor market, it starts to go down. And so in this case, age is kind of a classic definition of a confounding variable. It's something that's correlated with treatment status. It's also correlated with the outcome we are interested in. In fact, all of the collected variables would look something like this, where they're correlated with both the treatment and also the outcome. So in order to estimate things like the sample average treatment effect without any bias, we have to make a certain set of stronger assumptions. They're necessary to actually be able to estimate the sample average treatment effect. The most important is that we have to assume that all confounding variables are measured. That we basically, things like age that are correlated with both treatment status and also the outcome, anything like that we have to have access to. We have to have it in our data set. Formally, this is written as this. Both potential outcomes, y1 and y0, need to be independent of z conditional on x, where x is a matrix of all confounding variables that exist. The only problem is we don't know a priori what's a confounder, so we have to assume that we know all the things that are confounders and we've actually collected them. We also have to know the probability of receiving treatment must be greater than 0 and less than 1 for all individuals. This is something sometimes called the overlap assumption or the positivity assumption. You could write it like this if you're more technical. And why we need this is observational studies put way more weight on the statistical modeling procedures. We can't just plug in the group mean and use that as our estimate of what would have happened to the other folks. We have to use some heavier statistical machinery. And what this requires is we need to have somebody that looks, for everybody in the treatment group, we need at least one person who looks kind of like them not in the treatment group. Even if there's 100 people like that in the treatment group, there can just be one person in the control group and we can make that work, but we need at least one. We need some person who has the same characteristics that had the other course of action to understand what would have happened to people that look like this in terms of covariates had they gone down this other path. Finally, the SITFA assumption that I briefly referenced earlier also has to be satisfied. SITFA, all you need to know about it basically means that there's no spillover effect. Essentially, if I get the jobs training program, it does not change the outcome of somebody in the control group. When I try to teach this stuff, the example I always give is, say it was like, say I had a roommate and I got the jobs training program and my roommate didn't, and my income goes up. Maybe that influences my roommate in certain ways. Maybe he sees that my life is changing as my earnings go up, and then maybe he takes more classes or tries to apply to new jobs, and that increases his earnings as well. So we're assuming things like that aren't happening. So again, when these assumptions are satisfied, observational studies they collapse down to a simple statistical modeling task. It's a very similar equation as before, only now we have to condition not only on z, which is very easy to do, but also on x, which represents many, many, many variables. Sometimes it could be 50, 100. I've seen one observational study that adjusted for 600 things. So this x can be really, really complex, and this becomes a really difficult statistical modeling task. The most important assumption, though, and the one that gets the most attention in this space, is that all confounding variables need to be measured. This is generally the biggest critique of observational studies. Whenever you present one, people say, well, did you measure or did you adjust for, say, motivation, or did you adjust for income, or things like that? People have a preferred variable they'll usually throw out as a critique. And so Lalonde uses a linear regression that adjusts for all of these things, and this is the result. It found a very different conclusion than the initial RCT. So here, for just doing the observational study, we'd have a harder time arguing for the broad-scale implementation of such a jobs training program. And so red dashed line here is 0. And so there's a pretty high probability that maybe the effect is 0 or even could be below 0. We can't really make a strong claim with confidence that this jobs training program is necessarily on average going to increase your sample average treatment effect. Again, I can say stuff like that because here I'm going to kind of think through the Bayesian paradigm. If you're a frequentist, you could make different claims that are similar but a little bit more, a little less clear. But it applies kind of regardless of your philosophical framework. So what was the conclusions from the Lalonde study? And this is the important part. So Lalonde did this and basically concluded that, yeah, observational studies don't work because we can never really collect all of our confounding variables. And it was this structural assumption of this. It's called the ignorability assumption. Sometimes it's called all confounders measured. There is some confounding variable that we did not measure. Maybe it was real earnings in 1973. Maybe it was motivation. Who's to say? And in light of Lalande's findings, the field of econometrics initially argued to abandon observational studies. And this study, even though there was already a movement kind of going in this direction anyway, this really propelled a focus on natural experiments, things like instrumental variables, regression discontinuity, difference in differences, et cetera, et cetera, et cetera. These are all natural experiments methods that do not make as strong of a confounding assumption. They don't necessarily assume that you've had to measure all your confounding variables. Instead, they just make different assumptions that are equally strong. If you're a fan of instrumental variables, we'll have to have a conversation about the viability of the exclusion restriction. They're trading assumptions. But there was a big focus that this is not going to be satisfied, so we're going to take these other types of assumptions that, at the time, we believe are probably easier to satisfy. The only issue with this is there's another possible explanation. It's possible, in fact, that we actually did measure all of our confounding variables. We just did not sufficiently condition on them. That essentially we had all the confounders, we just didn't adjust for them in the right way. And so what do I mean when I say this? This is some simulated data I made. It's fake. Because it's fake, I actually know what the correct answer is. In this case, it's negative 4.2. Why is it negative 4.2? It's a number I liked. And so we see this data. It's very nonlinear. And I threw a linear regression on it. So this is the wrong statistical model. But it's a randomized study here. And because of the balance principles, we can see that there's kind of equal representation between the red and the blue, kind of across X. And so at each level of X, we have an equal number of blue points, people in the control group, and red points, people in the treatment group. And what this means is I can fit the wrong model, but it's going to miss in the same way equally between the two groups. And so my estimate for the SATE here, negative 4.4, very, very close to negative 4.2. Coverage properties are good. This is kind of exactly what we want. And a claim that is oftentimes made is the functional form, basically the type of model we use for randomized studies, isn't particularly important. There have been some critiques to this. Friedman in 2008 made a kind of critique to this claim. There is a rebuttal by Winston Lin in 2013. Just want to point out that I'm skating over a lot of complexities, but at a high level, we don't lose a lot of sleep over misspecifying the functional form of our models in randomized studies. Much different in the observational case. So in the observational case, balance is no longer guaranteed right off the bat, assuming randomization is pristine. Because we don't have randomization here, there's different frequencies of red and blue points across X. So if you look at on your bottom left of the screen, there's a lot of red points relative to blue points. And as X increases, there's systematically more and more and more blue points and less red points. And so here, I've again fit the wrong model. I've imposed kind of a linear structure onto this clearly nonlinear relationship. And now I'm paying a price for that. So my estimated sample average treatment effect here is -8, where I know the truth is -4. So here I'm missing, contextually, I'll tell you this is a lot, because in this example, it actually is quite a lot. And so what this means is the type of statistical model we use for observational studies has a lot of consequences. And so actually what happened is there were some economists that were taking a causal inference class by somebody who was talking a lot about this problem at the time. And there were a lot of methods proposed as kind of alternatives to linear regression, most notably propensity score matching. So there's some folks taking this causal inference class. They're talking about propensity score matching, which is oftentimes pitched as a way to relax these kind of modeling-based assumptions, particularly the assumption of linearity, drawing a straight line to things that aren't linear. So propensity score matching is a method that is going to relax that, in some cases by a lot. And so some econometricians were taking this class. They were talking about propensity score matching. And they kind of, the professor at the time actually was one of the folks that invented propensity score matching. And so they're like, oh, we want to break this model. We're going to use that on the Lalonde data. Before I show you what happened, the quick logic of propensity score matching is you're going to try to fit a model on the treatment assignment. Basically, who are the people that are more likely to get the treatment? Who are the people that are less likely to get the treatment? You basically model that probability. And this is what the propensity score is. What is the probability that you receive the treatment? Because it's not random anymore, we have to kind of model this process. And once we have that, we can try to recreate a randomized study. We can basically systematically weight up or weight down people in the treatment group or the control group using these propensity scores. And the idea is we want to put more weight on people who are in the control group that are kind of underrepresented in parts of the space that look like the treatment group, and vice versa. If you want to do this in R, here's a very, very simple one. Actually doing this for real is much more complex, and there's a lot of detail that needs to go into how you specify your propensity score model, which is one of the critiques of this method. But the upshot of this is when all confounding variables are measured, we can estimate the propensity score, and we can use this estimate to fix the imbalances that exist in our data, and in effect, make an observational study look more like a randomized one. So in practice, what does this actually look like? In parts of the space where we have fewer blue points, we're really going to weight up those blue points. We're going to have them represent literally more people in the data set. We're also going to throw away points at part of the space. There used to be a lot more blue points over here, and we threw a lot of them out because we had too many of them. And so the decisions of how much weight to put on each of these points, it's based on this propensity score, which is, you could think of it as a one-number summary of all of your covariates together, or all of your confounding variables. And we can use that to recreate groups that look more similar to one another. And the idea is if we do that sufficiently enough, we've kind of recreated balance, and then we can fit the wrong model onto this, and it's going to be OK to estimate things like the sample average treatment effect. That's the basic intuition of things like propensity scores. There's been a lot of theoretical work, too, that you can prove analytically, that if you have a sufficiently correct propensity score, that you can perfectly estimate things like the SATE without bias. And there's a lot of nice theoretical work there, too. But so the upshot of this is these econometricians, they're like, we don't think this is going to work. We're going to do it to the Lalonde data to show that this method isn't going to work. And of course, it actually does. And this was seen as the big proof of concept for propensity score matching. It really propelled it as a method, made it very, very popular. Because a lot of the kind of classical observational study methods at the time, things like Heckman regression were used on this and it failed. But propensity scores looks a whole lot like the randomized study. And so this was kind of how propensity scores entered the scene. And were able to kind of fix the Lalonde problem. So in 2011, January Perrett introduced the idea of if the issue is kind of a difficult functional form, we now have these advances in machine learning. Why don't we just model the functional form right? Instead of having to rebalance groups to be able to fit the wrong model and be OK for things like the SATE, why don't we just use a non-parametric model? And so this has kind of spurred the idea of using machine learning for causal inference more broadly, where we're going to fit really nonlinear structures and can basically just directly estimate the outcome. Now, when this is used on the Lalonde data, it's a little bit more of a mixed story. So if we look at the actual point estimate, it's the closest to the randomized study. The uncertainty is really large for the machine learning case. And there's a reason for why that is. There's been a lot of work done on the Lalonde data to kind of explore why is it that some methods do better, why is it some methods do a little bit worse. The uncertainty is actually related to parts of the data set that did not get a lot of attention earlier on. I talked about this overlap assumption. The Lalonde data has some weird things going on with overlap, and machine learning methods are going to kind of let you know when you have violations of the overlap assumption. So that's what's happening here. So there's more complexity on this. The thing for now that I want to point out is machine learning, from a bias perspective, how close is this? Doing pretty well. Another constraint here is we know that this estimate is very good and has very good properties, but it's still an estimate. The constructed observational study idea, we still don't really know what the truth is. And around this time these machine learning methods were coming out, there was kind of a increased use of something called finite samples, or these simulation studies, where instead of doing things like constructed observational studies, what researchers in this space oftentimes do is they take a real data set, they throw away the outcome, and they simulate a bunch of fake outcomes. And by a bunch, I mean 1,000 or tens of thousands of different outcomes, each of which has its own different function behind it. And so you say, on average, I don't know what anything is going to look like if I actually analyze it. I'll see how this method performs against a vast variety of different types of data I could encounter. And the nice thing about this is you know the truth now. You know the true sample average treatment effect, and you can see how well it performs in it. This is some of a bunch of evidence in favor of machine learning for causal inference. All of these papers use this approach, where they do these simulation studies based on real data, throw out the outcome, make up an outcome, you know the truth, pretend like you don't know the truth, see if you can recover it. And so constructed observational studies is kind of the proof of concept for propensity scores. These finite samples simulation studies is kind of the proof of concept for machine learning causal inference. So all of this is a very important backstory to what I'm going to talk about now, which is called the idea of measurement and causal inference in observational studies. And I want to revisit some things that are oftentimes skated over about these examples. If we think closely about the variables in the Londe study, they're things that we can directly observe. I can observe somebody's age, maybe not by looking at them, but I can look up records of age. I can find people's birth certificates. And that's very easy to record. It's very easy to agree on what somebody's educational attainment is if you ask them how many years are they in school. Things like earnings, it's very directly quantifiable. These things are all recorded. We have agreed upon meaning of what they represent. Likewise, the simulation studies used to kind of support the machine learning methods, they inherently assume away measurement. Because we've started from a point where we have this data set and just generate outcomes from that data set, kind of by definition, everything's been perfectly measured. So epistemologically, a lot of the causal inference space has kind of assumed away issues around measurement, both through constructed observational studies and also through this kind of finite sample stuff. I should also point out, since the Lalonde constructed observational study, there were several others for propensity scores that had very similar results. And in those studies, they had very similar sets of covariates, things that could directly be observed, things like education, physical measurements on people. Some of these were in the health space, and they had a lot of measurements about biological processes, things like that. And so in practice, when this stuff is actually used in the world, propensity score matching and machine learning kind of approaches to causal inference aren't adjusting for things like real income or education, but for things like anxiety and motivation and political ideology. And these variables are a little bit different than things like age and education and real earnings. And they're different because we can't directly observe them in the same way. I can't directly observe somebody's anxiety or their motivation. And there's not a lot of, it's harder to agree on what does motivation really mean. And how do you know who is more motivated than somebody else? In statistics, particularly in measurement, these things are oftentimes referred to as latent variables. And we have to use a measurement process to kind of assess them. Things like self-reported questionnaires are used to assess these things. We'll ask people a lot of questions about symptoms of anxiety. We'll ask them a lot of questions about what pushes them or motivates them or their interests. And we'll ask them questions on a questionnaire about being conservative or liberal or certain political sentiments they might have. And so to understand this idea better and how it interplays with causal inference, we're going to consider a thought experiment. Suppose that we have a hypothetical meditation intervention. And say it's a large health system, and they offer this free meditation program to all of its members. And they want to estimate the effect of the meditation intervention on cortisol levels. I've picked cortisol levels for now because it's not latent. We'll talk about that in a little bit. But higher levels of cortisol, just know that it's bad. We want that generally to go down. It's the stress hormone. A lot of exposure to it can be damaging to health. We'll suppose that individuals, they can self-select into this meditation program. This is a classical observational study. For now, we're going to assume that anxiety is the only confounding variable. So I'm going to kind of give us the hardest part and say, what would happen if I knew there was only one confounder and we actually knew what it was in advance? So anxiety is all it is. It's the only thing that's going to influence who's going to self-select into this program. So how do we actually go about measuring anxiety? So unlike the confounders we've considered so far, we can't directly observe somebody's anxiety. I can't, and there's no record I can look to. I can't look up somebody's pay stub. I can't look up their birth certificate to see how anxious they are. I'm going to have to ask them some questions. And so commonly, there's a bunch of different instruments that are used to quantify this, and you ask a series of questions, and there's a series of different responses. So here are some excerpts of one such instrument. So we'll ask people things like, I find myself getting upset by small little things. And you rate your response to that on a scale of 0 to 3, where 0 would be something like never, and 3 would be something like always. So we're going to consider that we had 14 questions that looked like this. And each question kind of relates to maybe a different symptom or a different experience that we believe is a kind of representation of part of what it means to be anxious. So after we collect these 14 questions for all the people in our study, we have another question. How do we transform these responses into a measure of anxiety? What do we do with the responses, from a causal inference perspective at least? So we could sum up values from each item into a single score. This is something called sum scoring. If you want it to be a little bit fancier, you could fit an item response model that applies differential weight to the contribution of each item. So the idea of these IRT models is, let's say one of my items is, sometimes I get a little bit worried. And another one of my items is, sometimes I have debilitating panic attacks. Those two items shouldn't be treated equally if I'm trying to measure anxiety. There's probably a lot of people that would say, I feel worried about things kind of a lot. There's relatively fewer people that have debilitating panic attacks, and we don't want to treat those two things as offering equal information. Sum scoring implicitly does. It says these two things, they're giving me the same amount of information. Item response theory is going to put a different weight on each of those responses. In the causal inference space, we could just put all the items in. We could put all the responses into our regression of choice and say, we'll let the model figure it out. And then there's a way you could actually kind of combine all of these things together. And we could put individual items in, we could put IRT scores in, we could kind of put it all in, and again, very similar to the last one, let the model figure it all out. So the idea of measurement-induced confounding is this. In this case, in the measurement world, theta is oftentimes used to represent the true value of kind of the latent trait. So theta here is going to represent an individual's true anxiety. And this is the thing that we can't directly observe. And then theta hat is our estimate of an individual's anxiety through this kind of self-reported questionnaire. It's something that we can, theta hat we can compute by fitting our IRT model. It's our sum score if we're using sum scores. It's the values of all 14 responses if we're just putting in individual items. And so to estimate a treatment effect with latent confounders, we need to adjust for differences in true anxiety between those in the treatment group and those in the control group. So formally, I could say that I need to make y1 and y0 independent of z and theta. But we can only observe our estimate of anxiety theta hat. So in practice, when I'm fitting a statistical model, what I'm actually doing is I'm saying y1 and y0 are independent of z, and I'm trying to make them independent of z and theta hat. So even if they're highly correlated, slight discrepancies between theta and theta hat, you could think of it as model misspecification in theta hat, is actually going to translate into bias. And so even if they're correlated 0.98, 0.99, that gap between the two could introduce bias when I'm relying on this estimate to adjust for confounding. And this is the central idea of what I'm talking about when I say measurement-induced confounding. So does it actually exist? This is a newish idea because the measurement world and the causal inference world, they're very siloed. They don't talk to each other that much. And because of properties of randomization, we know that things like mismeasurement of covariates don't affect randomized studies. What happens in this kind of observational case, though? So to get at this, I did a simulation study where I obtained 40,000 responses to the Depression, Anxiety, and Stress survey, the DAS-42. It's a 42-item survey. 14 of the items are about anxiety. That's where I got 14 from. I fit a generalized partial credit model with the MERT package in R. This is one of these IRT-like models. Well, it is a RT model. It's not an IRT-like. So I used these estimated anxiety scores from my IRT model as a ground truth. So basically, I fit these things. I got an estimate of theta hat. But I said, this is actually just the truth. This is my true theta. Now, the nice thing about the MERT package is if you supply it with estimates of a theta or estimates of a latent trait, you can actually simulate hypothetical responses to a questionnaire. So I basically estimated something. I said, this is actually the truth. I'm going to call it theta. I'm going to put it into this function, and it's going to give me hypothetical responses to a questionnaire. And I can use this like data collection. So I actually, and I used the true values to also do the causal inference things. I basically used them to generate outcomes. I used it to determine who enrolled in this meditation program and who didn't enroll in the meditation program, et cetera, et cetera. And here's where kind of the actual work of, if you were actually analyzing this, here's what it would look like. I fit a new generalized partial credit model on my simulated responses. And this represents what you would actually do if you were analyzing data in the first place. So now I forget the fact that I actually know the true theta, and I estimate a theta on the responses generated from what I put into this model. And then I adjusted for theta hat. So I basically set up a situation where I know all the things we usually don't know, and I know what the right model is. I also made it so everything is perfectly linear. It's a nice linear functional form. So I know the true model here. And I wanted to see if I repeated this process thousands and thousands of times, where I'm trying to estimate this with the correct model, can I actually recover what I'd expect to recover from a causal inference perspective? And so we're going to look at what happened. Before I show you the results, I want to point out what we're looking for. So the x-axis here, it's bias. Bias is bad. It means on average we're far away from the truth by a certain amount. We want bias to be centered at the vertical black line. So if it's centered right at 0, that's good. Any diversion on either side is bad. The y-axis is coverage rates. Because I did this thousands of times, I did it 10,000 times, I can estimate uncertainty from my model and see how often did these kind of uncertainty ranges correspond to the actual correct value. And so we want, I used 95% as my coverage threshold, which is pretty conventional. And so we want things vertically to be at this horizontal bar. So here's what happened. We definitely have some bias, and we have no coverage. So in none of the simulations did we cover the truth, and in all simulations, we are a little bit biased. I want to point out that these are coming from, I used an IRT model to simulate my data, and so the IRT estimates should be the best, which they were. They were still biased, and they still didn't cover anything. And so this is a pretty extreme finding. We would not expect to have 0 coverage. And so the question is, what happened? This is not good. In fact, it's really bad. We're basically saying that 95% of the time we'd expect something to happen, and it happens 0% of the time. Now, this is what I just presented is a more simplified version of a more complex simulation study I did. Here's the results from the full complex one. Panel 1 is a version of what I showed earlier. In the actual study, I explored other types of assignment mechanisms, like maybe individual items led people to be in the treatment, but the outcome was determined through the latent thing. That's what happened over here. Things are better in this case because we technically don't have any real confounders. It's more complicated. This is the setting that the machine learning world is kind of in, where we directly simulate outcomes directly from items, and we don't really think about things like measurement. Here, the item-based performance looks exactly how we want it to do. The important thing is in the real world, I suspect we're oftentimes over here. We actually believe that true levels of anxiety are what lead people to pursue a meditation program or not to pursue a meditation program. And that actual baseline anxiety is what influences cortisol, not literal responses to a form. We think it's actually the anxiety, not how you answered the form, which is over here. If we make the survey worse, the results get more extreme. So the psychometric properties of the measure I used are actually very, very good. I tweaked that too and said, what if we add some items that are really bad? How does that change things? So I changed some of the IRT parameters in the actual simulation setting, and as you'll see, bias starts to go up. This is in standard deviation units, so things like some scores will really fall apart if you have bad psychometric properties in both these things. All of these are not good. 0.1 standard deviations is concerningly high, considering most social science interventions have treatment effects around 0.2 to 0.3. Knowing that a third of your treatment effect could be explained from measurement bias is not a good thing. So what can we do and why did this happen? And that's what I'm going to end on. I'm still working out how to fix this. But what I suspect is happening is there's uncertainty in our statistical model of theta hat. We're using a statistical model to basically transform responses from scores into an estimate of some true variable that we know exists, but we can't directly see. And so there's uncertainty in this model, but we're not propagating that through properly. If we just take our IRT estimate, plug it in, adjust for it, there's a lot of different IRT values that could have been for that person that we're not considering. And that's going to systematically lead us to overly confident estimates. Basically, we're just putting in means where we should be thinking about a whole distribution. And so what I'm working on now is kind of extending this and using Bayesian IRT models to explicitly try to model for the whole distribution of potential responses. And the idea is there's a lot of uncertainty of what we think that your anxiety could be, conditional on what you've told us. And we want to use all of that information in our analysis. And I'm still working on the actual implementations of this, but I suspect that will really help with the coverage properties. And if we actually account for all of the uncertainties of the things we're putting into the model, our outputs will be sufficiently uncertain. We actually want them to be more uncertain. Right now they're too confident, but they're confident in the wrong place. And so I suspect that will resolve that. Another thing is to re-examine the role of the sate. So the sate is inherently fixed in time. We basically only consider the causal effect for this group at this particular time. What would have happened to them? Now, measurement models inherently assume individual responses vary from one time to another. In the measurement world, people would not say that if you fill out the questionnaire on this day, your responses would be the same as you filled it out the next day. They assume there's variation in responses, even for the same level of ability. Even for the same level of anxiety, you'd assume that your responses would be different day to day due to some randomness. So in the causal inference world with SATE, we believe covariate values are fixed over time. So we actually would say that, yeah, we think that your responses to this questionnaire should be the same today as they would be tomorrow, as they would be the next day, in terms of how this stuff is getting adjusted. And this is what I was saying earlier on, when the space between these two groups is kind of large and there's not a lot of discussion between some of the assumptions of what the SATE means. Fortunately for us, there's other causal estimands, things like the conditional average treatment effect or the population average treatment effect. And these things have different assumptions about the temporality of information over time. And so moving away from things like the SATE and thinking about things like the CATE may be another solution. This is something that me and a colleague have been thinking a lot about too in kind of other respects, but related to this idea of, are we thinking about a specific point in time, or are we thinking about what if we did the same thing again tomorrow with the same people? We'd expect it to change a little bit. So thinking less about the SATE, which is very, very common in causal inference, but thinking more about more general types of average treatment effects is likely another solution to this. So that's what I'm working on, and would love to hear people's thoughts about it or questions. And I'll let you know how it turns out. Just in time, too. I have a charger in my coat pocket, but.
How have your causal inference colleagues responded to this?
Yeah, that's a good question. So my measurement colleagues have been more shocked by it than the causal inference colleagues. A lot of the causal people are like, yeah, that makes sense. In a lot of what happens there is it's like, we're used to kind of assuming things that are pretty extreme. Like, I don't know if I really buy that. Like, when I've done observational studies, I'm always really nervous that there's confounders that exist there that we haven't adjusted for. Like, and there's a whole line of work called sensitivity analyses that basically is like, hey, we're probably missing one. How bad would it be if we were? Like, how big would this thing have to be to change the direction of our effect? And so the game we're playing a lot in causal inference is we're going to assume all of these really unlikely things are actually true, and then can we still get the right answer? And it turns out that's pretty hard. So it's very focused, at least in the, I should also say too, causal inference is a really, really big space. This is specific to like the estimation causal inference world. There's the sub-pocket of it that I'm in. But I don't think people are particularly surprised that basically the idea is if you have two people whose true abilities are here and here, but because of measurement issues, they look like this, you're essentially comparing the wrong people together. You're making somebody who looks, they're different people, but if they look similar, we're treating them as the same, that's going to lead to problems. Yeah, so it makes sense intuitively in that camp. I think the measurement folks have been more like, what is this? And then I'll tell them some of the assumptions we make in causal inference, and they've said, like, that's crazy. So particularly at the state. I'll tell them about stuff with the cape, and they're like, OK, that makes more sense. And this is the idea of maybe moving away from the state into things like the cape. And what?
What's your finding of a temporal state model going to be?
It's not a state. We're just saying like there's other estimands that don't make the same thing. It's forthcoming. So it's a lot of that. It's yeah, we're working on the simulations now. But yep.
Are there ways to estimate if you measure enough confounding variables, or how do you know that you're not missing some confounding variable?
Yeah, so that's the idea of a sensitivity analysis, essentially. And it won't tell you if you missed one or not. So a lot of the short version of a long story is this is the issue that happened with smoking cessation stuff, or when it came out, like in the 50s, when epidemiologists said that cigarettes are probably bad. A bunch of the people that started statistics who weren't good people, like R.A. Fisher and colleagues, had a lot of problematic thoughts on a lot of things. So R.A. Fisher, one of really invented a lot of early stuff in statistics. He loved smoking. And so the tobacco companies basically like had him as an expert witness, and he'd say like, oh, no, these are just associations. There's some confounding variable. And I think he's like, there's some gene that makes you really likely to get lung cancer, and the same gene makes smoking extra good for you. No, this is literally what he said. And so the idea of a sensitivity analysis is there was an epidemiologist, also named Hill, but no relation to Jennifer Hill, I don't think at least. And he basically said, OK, I'll give you that. I'll give you there's this one confounding variable. How related would it have to be to lung cancer? And how related would it have to be to smoking to make this claim make sense? And it turns out it had to be like absurdly large. Basically, every single smoker would have to have this gene, and it would have to give you like a 90% chance of developing lung cancer. And there's just nothing like that that exists in nature, especially when you consider like the baseline risk of smoking and lung cancer, which is not as high as a lot of people think. It's still very high, but it's I think it's like a risk factor of like 15-ish%. Don't quote me on that. It's been a while since I'm out of the public health game. I used to know more of those statistics, but less so now. But so it'll tell you how big would something like this have to be to change it, but it won't tell you like we got them all or we're missing one. So it's not really a test. It's more of just how bad could it be if we give you that there's one thing we missed. Yeah. Yep. We'll start back there and then.
Going off of sensitivity analysis, or have you explored yet what level of measurement error would be tolerable?
I've been thinking about that. Yeah. So that's something else that I'm trying to work on more in the future. So the upshot is this is like the worst case scenario too, and there's certain things like I had a really big sample size, which will make me really, really confident. So I've done some preliminary stuff, and the good news is if you're working with smaller sample sizes, the noise is actually going to help you out a lot. So I suspect in most people's studies, it's actually not like an existential problem. Like you shouldn't go home and be like everything's a lie. I think your more noise is actually going to help make the confidence intervals bigger and can help with some other properties here. Because I did this in a way that I kind of noised it up and some of the issues went away. But from a statistical theory perspective, that's really bad. Like if you're like, our methods only work when we have a little data and a lot of noise, that's not a good place to be. But so I'm working on like a sensitivity model for this type of stuff for measurement error. Like how big would your measurement discrepancies have to be in terms of like correlations between theta hat and theta for you to really be concerned? And because that's some stuff that you can, there's more work in the measurement world of like how close is theta hats to theta and things like that you can map on. So that's stuff that I'm planning to work on in the next year. Yeah, and I'm collaborating with measurement people now going forward. So it's a more of a, I'm very much from the causal inference world, less from the measurement, even though I'm trying to learn more about that space. But I'm working with some measurement people. Yep.
Similar to how you simulated responses with an RT model, is there ways to include or add a dynamic functionality based on time? Like you mentioned, like the responses to an anxiety survey might change.
Yeah, you could build that into your DGP, your data generating process. You could build that, and we've done that in the other work where we thought of like what it would look like to have these things vary over time. So you could plug that in too. Did you have a question, Andy?
Yeah. So you said that with the Bayesian IRT where
Yeah.
you're propagating uncertainty, that helps with coverage.
Yeah.
presumably.
What about
Does it do
bias?
anything- Yeah. Okay. That's what
The short answer is I don't know. I was thinking about this a lot today, but I think there's a way in which it could, in the sense of here's what I think is going on. So the uncertainty is going to be a lot different for different points in your data, and so if you do like proportional, if you put the whole distribution in there, I think what's happening is if you have like one person you're really unconfident in, and like three people you're really confident in, but they're all being treated as equally, if the unconfident one is wrong, it's gonna mess up the average.
Yeah.
And so think of it as like it should be a weighted average, but we're doing the weighting wrong, and that would cause bias. That's what my hope is that that all of it will fix it. If I get like perfect coverage but still biased, then that's gonna be another problem to solve. Also though, I mean, if I had to pick, I think I care considerably more about coverage properties than I'll take a little bias for better coverage. And it is I mean, I could get perfect coverage by just saying like we have infinite intervals. Not that quite, but I'd lean a little bit more on the coverage part of the bias variance trade-off than the bias part. From like a practical decision-making standpoint.
Here's a at-home question from Contrast from Vikram. What do you think of utilizing matching of units in observational studies and then restricting the average treatment effects to cohorts of matched units?
Yeah. So, I mean, that's less measurement-y, more just like general causal inference. So you do matching, and then you have. Can you reread the cohorts part?
Yeah. And then restricting the average treatment effects to cohorts of matched units.
Restricting the average. So it's like a multi-level problem.
I'm not sure.
Yeah, I'd have to. I'll talk with him the next time he's here about it.
Vikram, you have to come.
Yeah. I don't think I fully understand the context of it, or I think like the place my mind's going is probably different than the actual question. But Vikram, when you're here next, because I know you'll be here eventually, we'll chat about it. Yep.
Can you explain more on when you said the IRT theory is like applying differential weight contribution?
Yeah. So, like, how does it do it, or why would you want to do that?
How is it different?
Yeah. So, the basic idea is you want to see which, it's like, how much do you know about principal components analysis?
I think we learned that in our program.
Yes. Do you remember any of it? Okay. So like the idea of like a PCA would be you want to basically look at like which part of the feature space is explaining like the most variance. And you could basically think of this as like an unsupervised, like IRTs are essentially like an unsupervised method. And what you're going to do is say if there's some questions like I frequently feel worried about things, and that thing is kind of like a smattering of like that is kind of unrelated to all the other things. It's much more random. Like there's some people who are high in that who are low on everything else. It's probably not very discriminant of anxiety. But if you have a question like I frequently have debilitating panic attacks, if somebody answers highly on that, and let's say they answer highly on all the other questions too, that item is much more discriminate. And so IRT models will basically kind of sort through those and find things like that and weight them up. So if you're high on this thing but low on other things, that's not good from the IRT perspective. And if being high on this thing increases the probability that you're high on everything else, that's very good from an IRT perspective in terms of having a high theta value. That's like the intuition. Yeah, that's the intuition. Again, I'm very explicit. My expertise is less in the measurement space, more in the causal space. But that's the intuition probably to think about. There's if you want to read more about it, the MERT package, their paper is in Journal of Statistical Software, and they do a really good job of providing an overview. So I would probably read that paper, and they give like really good description of like they have all like the formal models written out too. So if you want to see like the actual mathematics of it, you can check that out.
Adding deliberately bad items to the questionnaire, can you give?
Oh yeah, so I just did that as so how I did it is so in these IRT models you have like there's two parameters. And one of the parameters is basically like how much information does each item give, and I could set that to 0, so I could make it a junk item. Like I made it basically not, your responses to this have no relation to the actual underlying thing. So when I say I added junk items, I'm doing it because I can generate ththings, and I just tweaked the parameter. In practice though, and I mean, so my first job, I did a lot, like I came from public health initially. And I did like some program evaluations and worked with a lot of like field folks and things like that. And it's like sometimes it's like you have, there's a lot of variance in survey design skills, let's put it that way. And you could have questions like, let's say I have a question for anxiety. And I kind of picked this one intentionally. Like a bad question would be something like, have you ever been stressed? Yes or no? Because everybody's going to answer yes. And answering yes isn't going to tell me a lot about your anxiety. So that's a bad item from like a psychometric standpoint, because it's not going to differentiate people who are high in something like anxiety from people who are low in anxiety. And if you're using something like a sum score that treats all of your items as equally relevant, that's not going to be good for you. Now that's probably an extreme example. The problems are things that like probably seem good but really aren't. And there's a lot of different reasons for why that is in terms of like wording and different biases, and like double-barreled questions are like a really bad, like things that make it harder for respondents to give responses, especially if that's correlated with like if it's correlated in such a way where it makes people who are low on the thing more likely to rate it higher, and people high on the thing more likely to rate it lower, which in theory it could. That would be like the worst case scenario. Like say if it was like our latent trait was anxiety, and you had some question that basically people who were more anxious tended to lowball it, and people who were not anxious or really low, like problematically low in anxiety, highballed it. That would be bad. Does that make sense?
Yeah.
Yeah, so that's what I mean when I say like a junk question. especially from the sum score perspective where you don't look at the contribution of an item, that's going to be really, really bad. Because then you have, it's going to make people look more similar statistically who should be treated much differently. Yeah, causal inference fundamentally is about, I want to match, for everybody like me in the treatment group, I need to find somebody who looks just like me in the control group. And if there's more of me and less of them, I need to weight them up. That's crudely all that we're doing. All the different methods are doing that in some way or another. The difference is in how they go about doing that. And so with that problem is if I have bad items and I'm using something like sum scores, it's going to make me look more similar to people who are not like me. And so the model is going to be like, you guys should get pushed together. So we're really different, but from the model's perspective, we're the same. And that's going to cause problems.
Yeah, makes sense. Thank you.
All right.
Thank you very much.
So just a few quick closing announcements, then we'll get our way to the bar. So first announcement, the bar will be Malthouse. We have not gone there yet. Nicole says it's good.
We went there once.
We went there once. Was it?
I liked it. Oh, you weren't there then. You had to leave.
You went without me?
Yeah.
All right, we're going to the Malthouse.
That's what I said, and you're like, no. I actually told you that before, and you vetoed it.
All right, so we're going to Malthouse, where I've never been, but they have. All right, Malthouse on Thompson and something. Again, if you don't drink, just come out and hang out and have fun. Come back February. We'll announce February in the next day or so. It'll be the second or third week of February, all about subway mapping, which will be a lot of fun. Thank you, George, both for speaking and getting us this awesome space time and time again. Thank you, George, everyone. And before we go to the bar, we have 2.5 pizzas left. We need to finish them every last slice. Everyone go up and do your part.
Nobody leaves.
Nobody leaves. Nobody leaves. And then we're going to go to
the door.
Then we're going to go to Malthouse afterwards, all right? So see you folks later. If I don't see you at Malthouse, see you next month. Thanks for coming.